So after talking about ways we could use rules to manage our server demand and capacity, how about we talk about the latest innovations in machine learning? And that's exactly what we're going to do here with the auto-scaling using machine learning, which Yahav here is going to join me. And let me tell you what, he has got the inside curve on how to use machine learning and data to automate all these processes.
Hi, I'm Yahav Biran. I'm a gaming specialist in AWS, and we're going to talk a little bit about how we are auto-scaling using machine learning. Now, what is the critical business issue that we face right now? So, the first thing that you want to avoid is to have players waiting in the lobby while they want to play, right? And so, while doing so, you want to have enough capacity to serve those players. Now, if you over-provision, then you pay more than what you needed, right? Now, if you want to manage those provisioning, under-provisioning or over-provisioning, you need to have a manual modification, and insert manual modification into your system. And this is also undesirable. So these are the three critical business issues that we are going to help now. Before we continue around how about how we are going to solve this problem, let's talk a little bit about how are we scaling, right? So we're using game servers. Game servers are the things that serves your players, right? But then on the other hand, we have EC2 instances. EC2 instances are the components that you are paying for, right? So these are the two dimensions that we're going to discuss right now. You are going to ask us for game servers, and we are going to charge you for EC2 instances. And the way that we do it is that we are packing game servers upon request on top of an EC2 instance. And once this EC2 instance gets filled, we're spinning up another instance. And that's what we call horizontal scaling. Now, when we're looking at auto-scaling, the problem that we have in auto-scaling is scaling down. Scaling up, it's easy because basically you need more capacity, you actually feel the pain, and then you ask for more capacity. But scaling down can be impactful, right? It can break things for our players, and we need to be more smart about it. Another aspect of challenges in auto-scaling is that if you are acting based on immediate events that are happening in your system, you're ended up doing reactive calls. And those reactive calls not always be the optimal calls. And we're going to talk a little bit more about examples. But just to give you the canonical example that we're going to solve is that if, for example, your matchmaking service, right, went down from some reason, you are not reacting immediately into these events. You are basically know how to predict what you need, even if an event like an outage in your ecosystem occurred. What we see here is an example of the game server autopilot, as we call it, right? If you look at the yellow plot, this is the actual game servers that are running, right? They are not necessarily serving users. They are running and ready to go. And the green plot is the used game servers. These are game servers that are actually being played against with players in this specific region. Ideally, what you want is that your allocation and usage will ride smoothly at the same curve. By doing so, you are going to pay only for what you use. But then, if we go back to the outage issue that we discussed before, look at those drops. These are events of an outages in the matchmaking service. So if you think about this specific example, you ended up, if you are reacting and you're not using machine learning, you at this point releasing a huge amount of resources that you will need in the next 20 minutes. So this mechanism helps you to be smart around the allocation and about scaling down, specifically about the scaling down events. Make sense?
Sure does.
Now,
let me ask you, I got a good question here.
Please.
So Yahav, I got a good question. So much fidelity are we able to achieve with machine learning to make that curve happen? Because I see some anomalies, I see some edge cases in here, like we've got these hard drops, right? And it's got to be hard for a algorithm, just crunching data, to really know how, when is the acceleration on that curve fast enough that I need to make an adjustment, and when is it an anomaly, and how to identify those spikes?
It's a great question, because when I just started this project, I was looking just simply at history of events, right? I was looking at previous usage numbers. And by looking at previous usage number, it was very simple because I used just linear regression, and I didn't need all this complex machine learning system. But then I ended up having these false positive cases. Now I wanted to improve this false positive. And one of the ways to improve it is by adding more signals to allow this model to be more involved and be smarter. Now, and in this particular example, I started to look at average time in the lobby. So think about usage, and I also tried to look at how much time people are waiting in the lobby, at the average time. And then I saw that I noticed an improvement in the false positive cases, but it still was not optimal. And then I started to look at how many cancellation was triggered by users while they were in the lobby, right? And then looking at all these three dimensions and include them into one cohesive model, I was able to reach a much more accurate model. Yes. So just to give you an idea of how a system like that look like. So we started with, and I'm going to explain it throughout the data, a pipeline, a typical scenario of a multiplayer scenario. A player wants to play, it's contact a matchmaking service, and then it's getting matched into one of the regional clusters. Those regional clusters have this capacity available for your players, and then eventually this player is getting matched with other players, and they're playing, and they're having fun. Now, while this is happening, in the background there is a Lambda function that pull all these metrics that I discussed before: usage, average wait time, and the cancellations, and it's pulling it from this external system. Now, once that's done, it is persisting this information into a state. It can be S3, it can be DynamoDB. In this case, it's a DynamoDB. And now this DynamoDB is using to train a self-learning model. This self-learning model continuously getting information from this state and training, and use this data for both training and testing purposes. Now, once that this model is trained, this autoscaler, the autopilot component that sits in each regional cluster, are seeking for prediction from the model. And once that they are getting this prediction, they are simply setting the capacity that the model told them in each regional cluster. Now, if you look at this architecture, this is a pretty extendable architecture. You can replace this thing with any system that you have in your ecosystem. Matchmaking is an example, but if you're an MMO and you don't have a matchmaking, you have something else, that's perfectly fine. If you have other system that can emit a meaningful metric that can help you to drive the capacity, that's perfectly fine. So this is an extendable approach here. You can also replace each component here to do whatever you want, right? You can use SageMaker, you can use Forecast if you don't have the knowledge of data scientists in your organization. This is perfectly extendable model. Now, I wanted to call out that this is an autopilot system, right? Autopilot system does not supposed to always, that's supposed to cover all the cases in the world. And that includes turbulence, right? In case of a turbulence, you want to have the capability to take the wheel and drive it if you see a weird spikes, a marketing campaign, because this is like an autopilot on steady state. So we enable you a dashboard that allowed you, that that reporting all these metrics across the system and enable you to monitor and take control if you choose so. Now, the final part that I wanted to make to make here is that the autopilot system that we are offering here can work with any system that you want, any orchestration system. If you use GameLift as you just reviewed before, GameLift is a system that can work with autopilot. EC2, EKS or ECS, if you use containers, is also something that can work with autopilot.
So if I understood correctly, let's see if my brain can put this all together. Through machine learning, I gain great efficiency in my day-to-day operations because it's going to be able to follow all of this data. It's actually one of the great modern cases of innovation in data and the way we're able to see data across different horizons and pull it together to make different use of it. But then I also have the ability to step in and go, wait, the marketing team just ran a big promotion and we're about to get hit with 50,000 concurrent users. It's not going to understand, it's not going to recognize it soon enough, so I'm going to fix that real quickly, and then once I'm back on tune, go back into my autopilot.
Exactly.
So there you go, that's what machine learning is going to do for us. It's going to make all of our gaming better, and that's why we're at Game Tech, always trying to innovate for customers, always trying to help developers dream big and build bigger. Stick around, we're going to be back with more from the booth here at GDC 2019.